Hello everyone, welcome to the soft computing lecture series, and we are doing the fuzzy logic. So we have seen about the classical sets and the fuzzy sets. Now we continue with the same theory ahead with classical relations and fuzzy relations. In today's session we'll see what are fuzzy relations, what are classical relations. So before starting with relations, we need to have some concepts about the Cartesian product. So the Cartesian product of two or more sets is not the same thing as the arithmetic product of two or more sets. So now we study what is the meaning of a Cartesian product, and from Cartesian product we will study the relations. But in this session we will study about the classical relations. So these are concerned with the classical sets, classical relations, and not with the fuzzy one. So suppose we have two sets. So these are two classical sets, A and B. So we have these two sets A and B. Now how to find the Cartesian product? So this is actually the symbol for Cartesian product, A into B actually, and this is BA, AA and BA. How to find the Cartesian product? So suppose we have, these are the two sets. Let us see how to find the Cartesian product. So this is A and B. So with A and B, we first take the first element of A. So this is 0, and then combine with A. Okay, so we have OA, then combined with B, so we have OB, combined with C, we have OC. Then the next element is 1, so 1 with A, 1 with B, and 1 with the C. So this is the Cartesian product of A, B. And we want to find for BA, so we first take the element of B first. So the first element of B is this A, small a. So this small a with 0, small a with 1. So we have A0, A1. Then the next is the small b. So B0, B1, C0, C1. Then with A, the Cartesian product. So because we have both are A, so first is we only have two components in A, two elements in A. So 0 with 0, 0 with 0, 0 with 1, 1 with 0, and 1 with 1. And B with B, because there are three components, so we have A, B, AC, BA, BB, BC, CA, CB, and CC. This is the Cartesian product, how we have the Cartesian product. Now let us see the relation. So what are crisp relation? Now crisp relations, they are the subset of Cartesian product. Now consider we have two crisp sets. So these are the two crisp sets, X having component 1 2 elements 1 2 3, and Y element having elements A B C. Now this is the unconstrained relation. This is a relation. We can just define the relation by this. Okay, now here this in this case we have, when we take the, we find the relation. So relation is given by this symbol, and this, suppose R is the relation. So we have this 1A, 1B, 1C, 2A, 2B, 2C, 3A, 3B, and 3C. This is similar to the Cartesian product. We can say all the terms are here. So that why it is called as this is actually an unconstrained relation. Now what do we mean by constraint relation? In case of constraint relation, maybe like we can have this as 0, so this is not allowed, and this pair is not allowed, and this pair is not. Maybe like we can have like this. So in unconstrained relation we have all the terms. Okay, if you take the Cartesian product of this, what we have is 1A, okay, 1B, 1C, and 2A, 2B, 2C, 3A, 3. So all are present. Okay, so all are present. Now we also have something called as sagittal diagram. So this is the sagittal diagram. So we have X, we have three elements 1 2 3. Y, we have A B C. So we are taking this A with 1 with A, 1 with B, 1 with C. So all are present. So therefore we draw a line then this way, and the second one from 2 to A, 2 to B, and 2 to C. And then finally we have from 3 to A, 3 to B, and 3 to C. This is how we draw the sagittal diagram. Now we can also have this constant relation, can be of all the four. We can also have the constraint relation. The previous what we saw is unconstrained relation. This is the constraint relation. So we have the elements 1 2 3 A B C. Now you can see this is 0. Okay, in the previous case this was 1, but here it is 0. This is also 0. This is also 0. This is also 0. Okay, so due to some constraints, this pairs are not considered. And if we draw the sagittal diagram, so from this we can draw the sagittal diagram that from A we only have BC. So from A we only have B and we only have C, and from 2 we have A and B. So from 2 we have, this is A and this is B, and from 3 we only have C, so this is only C. Okay, so this is the sagittal diagram. So this is a relation. Now special cases of constant and the unconstrained Cartesian product for sets where r equal to 2 are called as identity relation and universal relation respectively. We will see this, what is the meaning of identity and relation and universal relation. So for example, this we have this A, this example is given here itself. So if we have A equal to 0 1 2, okay, now the universal relation denoted by UA, this is given by this, so all the pairs are considered in this case. So this is actually A with A, so but all the terms are considered. So 0 0 0 1 0 2, okay, 0 1 0 0 0 0 1 0 2, then we have 1 0 1 1 1 2, 2 0 2 1 2 2. So all the terms are considered. So that is the universal relation. Now what is the meaning of identity relation? In case of identity relation, we only take the pairs where both the terms, both the elements are same. So this we consider this one, we consider this one, okay, and this 2 2. So this, whatever the thing we have, this is the identity relation. Okay, so this is the universe, this is the identity relation, this is a special case. Now cardinality of the crisp relation. Now suppose n elements of universe X are related to m elements of universe Y. If the cardinality of X is suppose nx and cardinality of n is Y is ny, then the cardinality of the relation R between the two universes is given by this. Okay, this is how we get multiplying them, and the cardinality of the power set is given a 2 raised to nx into ny. Okay. Now what are the operations which can be performed on crisp relations? Suppose we have R and S, two separate relations on Cartesian universe xy. So union, when we take the union, okay, it is of course similar to the what we have done in the case of sets. We take the maximum of them. Okay, we take the maximum whatever we get. Let us take one example. Okay, like suppose if we have R as a relation, we have R relation is given by suppose this 0 1 0 1 1 0. This is suppose R, and suppose we have S as another relation. Suppose S is another relation, we have, so this is suppose S. Now if we take the union of this, okay, so when we take the union of this, what we get the maximum of this two, union for union. So this is the first element, this is the first element. Now 0 1, okay, we take 1 because 1 is larger, and there is 0 1 and 0, so 1 is larger, and then 0 0 we take 0, and here 1 0 we take 1, 1 1 we write 1, 0 1 we write 1. So this is the union operation. Similarly, if we want to take the intersection operation, okay, so intersection, of course, in case of intersection we will take the minimum. Okay, so in this case, if this is actually if we want to take the intersection of these two relations, then we take the minimum of this. So this is 0, this is 1, so we write 0, then 1 0 we write 0, 0 0 is 0, and here again 0 1, so 1 0 is again 0, 1 1 1, and here 0. So this is the intersection. This is how we do the operations. Then complement is of course as if you want to take the complement, you just subtract 1, or in other words we can like say make 0 as 1 and 1 as 0. And containment, okay, so R is a subset of S, then it means that all the elements are also less than equal to that S. Okay, so this is how we have the 4 operations. Now we have some special relations. What is a null relation and complete relation? Now phi, if we define phi as a null relation, then all the elements are, you can see, 0, and complete relation means all the elements they are 1. Okay, so this is E and this is phi. Now properties of crisp relations. The properties of crisp relations, just like we have commutativity, associativity, distributivity, involution, idempotence. Whatever properties we have done for crisp sets, the same holds good for crisp relations. Also, the De Morgan's principles and the excluded middle axioms are also hold good in case of classical relations or crisp relations. Now the null relation, actually this is phi, and the complete relation E are similar to null set and the whole set respectively. Okay, so now next thing is the composition. Okay, we have to take the composition of two crisp relation. Okay, now suppose we have a relation R which maps elements from X to Y, and we have another relation S which maps from Y to Z. Okay, so we have a relation R which maps from X to Y, and we have another relation S which maps from Y to Z. So you can see Y is common between them. Okay, so we can find a relation T. So we can find a relation T having elements in universe X that R contains. Okay, this one. Okay, and the same elements in the universe Z that S contains. Okay, so we can find a relation T such that it contains the elements X from R and Z from S. Okay, this from R and this from S. Okay, so Y will not be there. Okay, we can say Y is acting as a bridge to create a relation between RS such that we have in that relation we have X to Z. Y will not be there. Y is just acting at a bridge, we can say. Okay, now composition, this is actually called as a composition. Whatever operation we are doing is called as a composition. Now consider this is these are the two relations. This is R relation defined in from X to Y, and this is relation S defined from Y to Z. Now there are two forms in which we can find the composition, or we can perform the composition operation. One is the max mean composition, other is max product composition. Now in case of max mean composition, what we do, we write this is the symbol how we just express the composition. Okay, and this is the operation. First of all, we take the AND operation, okay, of the values of the elements, and then we take the OR. Okay, so in inner product we take this this is why it's called as max mean. First we take the mean and then we take the max. So let us instead of getting confused in this, let us try to solve a problem. So suppose we have this these are the two relations which are, now we need to find the composition of R with S. So this is denoted by T equal to R of S, that is the composition of R with S. Now these two relations, they are actually constrained relation. As you can see, there are zeros as well as ones. So how to find this? As we know, this T, whatever the T we get, the composition of RS, it has components from X and Z. Okay, so sorry, this is X1, X2, X3, okay, on this side, and here we'll have Z1 and Z2. Okay. Now how to find these elements? So we take the max min composition. So what I do is, so I write max, and then okay, now see this is the first row of this, and this is the first column of this particular R, and this is S. So first row of R and first column of S, the first element, this is 1, and we take this as 0. So what we take is mean of 1 0. Okay, mean of 1 0. Okay, this is the first element. Then second element is this one, and this is the second element of S. So mean of 0 0. Then this third element of this and third element of from this particular column. So we have to write mean from 1 and 0, and then finally this and this both are 0. So mean of 0 0. Now mean of 1 0 is of course 0, mean of 0 0 is also 0, mean of 1 0 is 0, and mean of 0 0 is 0. Now out of this 4 we have to take the max, because last operation is max. Now max, because there is no max, all are 0, so we write this is the first element, this is 0. Okay, now how to find the second element? Okay, now to find the second element we do the same thing, okay, but in the different way, like we write the max. Okay, now this is the first row and the second column. Okay, in this case we take the first row and second column. So again, mean first element 1, first element 1. Okay, then first element from here, first element from here, mean of this, sorry, second, then mean from this, and mean from this third one, and finally 0 0, so mean from 0 0. So mean is, of course, both are 1, so mean is 1 itself, and here we have 0, here we have 1, here we have 0. Now we have to take max of this 4. Now because 1 is the maximum, so we write 1 here. Similarly, we perform all the things for all the rows and columns. For the second x2, what we take the first row, first column for this element, okay, and first row, second column for this element, and finally for x3 z1 it will come here, and x3 z2 will come here. Okay, I will just write the values. I have done this. Okay, I will directly write the answer. So if we do the calculation, we will see this is 0 1 0 0 0 0. Okay, so this is what we get the last. Okay, so that's all for this session. Thanks for watching.